All right, so let's go through number 40 again. So here it says, what is the maximum number of electrons in an atom that can have the following quantum numbers? N equal to 4, L equal to 1, M sub S equal to positive 1/2. So N of equal to 4 is the energy level, L equal to 1, that's a p subshell, and so 3 different orbitals can have electrons that have a positive 1/2 or a spin up designation. So that means that there should be 3 electrons that each have N value of 4 and L of 1 and M sub S value of positive 1/2. So 3 is your answer there. Number 1, you're balancing chemical equations. So here we have 2 sulfur atoms, we have 4 hydrogen atoms, we have 2 oxygen there and there, and we have 3 sulfur. 3 here, 1 there, and 2 there, so that adds up to 3. Part B here, we have 6 oxygen on the left, we have 4 plus 2, 6 on the right, 4 hydrogen on the left, or on the right, 4 on the left, 2 carbon on the left, 2 on the right, so this is balanced. Here we have 2 carbon on both sides, 2 nitrogen on both sides, 14 fluorine there, we have 8 here and 6 there, so that makes 14, so now we're balanced. All right, number 2, it says household ammonia. It's used for cleaning. It contains about 10 grams of ammonia in 100 milliliters of solution. What is the molarity of the ammonia solution? So molarity is equal to moles of ammonia over liters of solution in this case. So we have to figure out the number of moles, we're given grams. So 10 grams of ammonia, the molar mass of ammonia, we derive that as 17 grams per mole. Okay, so here we have to find the number of moles. Okay, so moles over the total volume of the solution. Here they gave us volume in milliliters, so we convert that to liters by dividing by 1,000 or moving the decimal place over 3 places to the left to get 0.100 liters. Divide to get 5.88 molar for the concentration of ammonia. Part B, if 40 milliliters of a 0.255 potassium sulfate are added to enough water to make 135 milliliters of the solution, what is the molarity of the diluted solution? So when we have a dilution problem, we use the formula M1V1 is equal to M2V2. Molarity times volume before is equal to the molarity times volume after, and so if you cancel out the units, it's really what we're saying is the moles we have before is equal to the moles we have after of the solute. So initially we had 0.255 molar solution, so that's M1. Our initial volume of that was 40 milliliters. And then they diluted it to a total volume of 135 milliliters. Now notice I didn't convert milliliters to liters. It's not necessary, okay, because the units are going to cancel out as long as they're both milliliters. Units cancel, you're left with molarity anyways. So you just solve for the diluted molarity. In this case, it's 0.0756 molar for the diluted solution. All right, number 3 here, it says assume you have 1.35 moles of sucralose, the active ingredient in Splenda. How many grams of sucralose do you have? So you're starting out with 1.35 moles of sucralose. You have to find the molar mass of sucralose, which you do like we did earlier, multiplying the number of atoms times its average atomic mass off the periodic table, adding those together to get the molar mass of the substance, which in this case is 397.5 grams per mole. Convert moles to grams to get the mass of sucralose in grams. And then part B, how many molecules do you have? Well, I can start back at my given information. I have 1.35 moles. So I know I can convert moles to molecules using Avogadro's number. So when I do that, I get 8.13 times 10 to the 23rd molecules. And then part C, how many moles of carbon do you have? If I have 1.35 moles of sucralose, for every 1 mole, there's 12 moles of carbon. How do I know that? Well, there are 12 atoms, okay? In the molecules, there's 12 moles of carbon per mole of sucralose. And so, do the math, I get 16.2 moles of carbon. All right, point 3, you have 7 questions, 7 of the 12, so of course I've done all 12. You can choose which ones you prefer to do. So number 1 here, it says determine the formal charge on each atom of the following molecule. So here I did that for oxygen. So it has 6 valence electrons, and it has 6 electrons here represented, 4 for lone pairs, and then 2 here for 1 for each covalent bond. Sulfur also has 6, so it has the lone pair, which is 2, and then each covalent bond is 1, so 2, and then 4, and then 5, and then 6. So you have 0 formal charge on the sulfur as well. For the second structure here, I have 1, 2, 3, 4, 5, 6, 7, so I have a -1 formal charge on my oxygen. Here I have 6, 1, 2, 3, 4, 5, 6, so it has 0. Sulfur has 6 valence electrons. 1, 2, 3, 4, 5 is only represented there, so it's +1. All right, the next question for part B, it asks, based on your results, circle the more probable structure. So we know that the structure that has the least amount of formal charges would be the more probable, and so that would be the top structure here, and it's circled. Part C, what is the geometry of a molecule? So if you go back and look here, we have 3 electron pairs, 1, 2, 3. Okay, so its electron pair geometry would be trigonal planar. Okay, but because it has 1 lone pair, it ends up being bent. Okay, and so the bond angle for a bent configuration is it's going to be less than 120 degrees. All right, so next one, number 2 here. Here we have a reaction. We're given 3 moles of ammonia, 4 moles of oxygen. They're asking what's the limiting reactant here, or the reagent. So here, before, I can pick any product to convert this to moles of ammonia to moles of NO or moles of water. So why did I pick NO? Well, if you look further in the question here, it's asking what is the theoretical yield of nitrogen monoxide. So what I'm going to do is I'm going to convert everything to nitrogen monoxide. That's going to save me a step later on. So I'm going to convert moles of ammonia to moles of nitrogen monoxide, moles of oxygen to moles of nitrogen monoxide. So I did that here using my molar ratio. All right, so for ammonia, for every 4 moles of ammonia, I can produce 4 moles of nitrogen monoxide. So I can produce 3 moles of nitrogen monoxide given the amount of ammonia that I started out with. And then for oxygen, same process here. For every 5 moles of oxygen, I can produce 4 moles of nitrogen monoxide. So when I do the math, I get 3.2 moles of nitrogen monoxide. Well, I have excess oxygen. I have ammonia is going to be my limiting reagent. So I list that there as the answer. What is the theoretical yield of nitrogen monoxide in grams? So I know I can produce 3 moles of nitrogen monoxide given the amount of ammonia I have. So 3 moles of nitrogen monoxide, I'm converting moles to grams. Using molar mass of nitrogen monoxide, I have to calculate that out. So I did that as 30 grams per mole. All right, so I convert that to grams of nitrogen monoxide, and that's how many grams I can make. It's, 90 grams of nitrogen monoxide. So that's theoretical. So now I have to figure out my percent yield. So percent yield, the formula for that is actual over theoretical times 100. This is my theoretical value I calculated. My actual is what I actually measure out in the experiment, and it gave me that value of 81.2 grams. So my percent yield is going to be my actual value, 81.2 grams, divided by my theoretical value, which is what I calculated, which was 90 grams, times 100, to give me 90.2%. And that's my percent yield. Number 3, here it's asking Draw Lewis structure, predict the geometry and the bond angles for it. So here we have methane, CH4. So this is the Lewis structure for it. We have carbon, it has 4 valence electrons. Hydrogen has 1. Okay. So it has 4 electron pairs. It has no lone pairs. Its geometry and its electron pair geometry are both the same. It's tetrahedral. The bond angle for tetrahedral is 109.5. Okay. So if you look at your table that I asked you to memorize here, the tetrahedral, this is the bond angle it's given to. Okay, so that's all in that chapter 7, the last section in chapter 7 talks about that. All right, part B, here we have PBr3. When you do the Lewis dot structure there, you have a lone pair on the phosphorus. So you have 4 electron pair geometry, so it's tetrahedral. But because you have a lone pair there, you're going to end up having trigonal pyramidal, similar to ammonia. So its bond angle is going to be less than 109.5 degrees. For CH3 plus, here this is the structure. It's positive. It has overall positive charge because it has 1 less electron. Okay, so it has an electron pair geometry of 3. Okay, so trigonal planar is its electron pair geometry, and because it has no lone pairs there, it's also its geometry, molecular geometry would also be trigonal planar. So the angle between the bond angles here are 120 degrees. And then for water, here we have 3 electron pairs. Okay, so if it didn't have a lone pair, it would be trigonal planar for electron pair geometry. But the molecular geometry is going to be different because it has the lone pair. It's going to be bent. Okay, so the bond angle is going to be less than 120 degrees. All right, number 4. Here it says determine the mass percent of each element of the food enhancer, monosodium glutamate, MSG. Here's the empirical formula. So here I have to find the molar mass of the compound. Okay. Once I do that, the mass percent is very easy after that, because basically anytime for mass percent is just equal to part divided by whole times 100. Right? So the part is whatever the element its mass is, divided by the whole, that's the entire thing, times 100. So I do that for every element. Part divided by whole times 100. Part divided by whole times 100. I do that for each element to get the percent, which is the mass percent. Okay, for each element in the compound. All right, so then it's asking me to find the molecular formula. It told me the molecular weight of the molecular formula is 169. So they gave me the empirical in the previous problem. I know because I calculated its molar mass of the empirical was 169. And they're telling me the molar mass of the molecular is also 169. So 169 over itself is 1. So the empirical formula and the molecular formula differ by a factor of 1. So basically it's the same formula. Okay, so that's your answer there for number 4. Number 5 here, we're trying to determine the oxidation numbers for each element in the compound. So here we know oxygen's -2. -2 times 3 is -6. So nitrogen must be +5. It has to add up to a -1. All right, because there's a negative charge there. Okay, so oxidation number is +5 for nitrogen and -2 for oxygen. For CO3 2-, here we have -2 times 3, which is -6 for oxygen. So carbon must be +4. I have to add up to -2 because that's the charge on the overall charge on the molecule. Nitrogen is +4 for its oxidation number, and oxygen is -2. For HiO3, hydrogen is +1, oxygen is -2. -2 times 3 is -6. So iodine must be +5. Oxygen is uncombined, so 0. Hydrogen is +1 times 2 is +2. Oxygen is -2, so it adds up to 0.